Okay, so good question about mathematical induction. So here, the question is asking us, given that n is part of the real number system, meaning that we're looking for z means integers, plus means positive. So 1, 2, 3, 4, 5. It should work for all positive numbers in the real number system. Which proposition can the initial statement for mathematical induction be proven? Now, remember, the initial statement is the test, okay? Because when we're doing mathematical induction, we use our acronym TAPE. Now, it is test, assume, prove, and evaluate. Okay, so we're only having to test here. So I'm going to check first. None of these things have weird stuff that makes it start somewhere else. Good. So we're going to be testing the number 1. So in these equations, we're going to check the number 1. Okay, so for the first one, x to the power of 2, 1 minus y to the power of 2, 1 is divisible by this, assuming that it's not equal to 0. Okay, so there we'll end up with x squared minus y squared over x plus y. Now, my intuition here tells me to do partial fraction decomposition, but that's just because I love the process. If you notice here on the bottom, the x and the y, they don't have the squared above it, so we're not going to bother doing that process. What we are going to do, though, is we're going to factorize the top of this expression. So I can see that I've got x squared and y squared, meaning that in these brackets, I would have had an x, and a y, an x, and a y. Now, there's no term in the middle, and this section is negative. Now, because I've done a lot of maths in the past, I know that that means one of these is a plus and one of these is a minus. If you don't believe me, you can test by expanding out your brackets. So x times x makes x squared, x times negative y makes minus y, x, y times x, so plus yx, so these two will cancel out. And then the last one is a positive times a negative, so minus y squared. So that's how we end up with that top part there. So over x plus y. Once it's in this form, I can see that this is a factor of this, meaning that yes, it is divisible. I'll get a nice number. So our answer for this one is A. But let's just go through the others to see what would happen if it wasn't A. Okay, so this one here, if I test the statement in B for it to be 1, that means my left-hand side is going to be 1 squared, and my right-hand side is going to be equal to 1 over 6 times 1 bracket 2 times 1 squared plus 3 times 1 minus 1. Now, when I expand this out, 1 over 6 stays at the front there. This will become 2, this will be 3, and that will be minus 1. So it'll be multiplying 4. The left-hand side does not match the right-hand side. So we've proved that it's not true. Okay, so it can't be B. This one here, we're proving that it is divisible by 3, meaning that when I substitute 1 into this statement and divide it by 3, I should get an integer or a whole number. So 1 plus 1 cubed plus 1 plus 2 cubed divided by 3. That will give me 1 here. 2 to the power of 3 makes 8. Plus 3 to the power of 3 makes 27 divided by 3, which will be 35 over 3. So that is not divisible by 3. It cannot be C. Okay, this statement here, when I let r equal 1 on the left-hand side, I'm going to let n equal 1 on the right-hand side. So 1 over 2 times 1 minus 1, 2 times 1 plus 1 should be equal to 1 over 1 plus 1. So the right-hand side is a half, and when you go through and solve the left-hand side here, that will end up giving you a third. So they're not right either. You could prove all the other statements wrong if you've forgotten how to factorize and get your answer for A.